Okay, let's get started. So I'm going to say it now, but I'm going to announce it at the end of class also. You have a quiz, so make sure to pick it up and then, of course, turn it in on Friday. So it's about pointers and smart pointers and that sort of thing. But I don't have anything else, though. Are there any questions before we start? Oh yeah. I can help you clarifications, of course, but like, what is the answer to question 1 part D? No. Yeah. Other questions? Okay, so last time we started talking about things about C++ that separate it from other languages, and this is where C++ really shines above other languages. So before this, other languages pretty much have everything that we've already learned so far, but this is where the roads diverge. So the first things we saw were this thing called the copy constructor, which is where I could copy data over from another object instead of having the user do it themselves, which is pretty useful. But of course, other languages also have copy constructors. But what makes this even more interesting is in the case of operator overloading. So operator overloading says, instead of having to call a function on an object, so maybe I want to add 2 matrices, I could say this matrix dot add this other matrix, then I could do that, but it's a lot more readable and maintainable and easier on the user to just say plus, because they know what the plus actually means instead of having to call this function. So if it makes sense, then you may want to overload an operator. So you could say operator plus to mean I'm going to overload the plus operator, whatever this means. And you can define it between whatever type you're working with, say a matrix, and any other type at all. So the usual one for addition probably would be a matrix, but if you had multiplication for matrices, then you can have a matrix times a matrix or a matrix times a vector. So it depends on the use case, but it can improve readability quite a bit. So basically we went over how do you declare the overloaded operator, how do you actually use it, and then once you use it, the code becomes a lot easier to read. You can do the assignment operator too, just by instead of saying operator plus right here, you say operator equals. And then what you can do as a result of that is instead of like say constructing an object and then copying the data over, you can just do the assignment operator and it looks much better that way. It's a lot easier to work with too. Yeah, so and some notes about that. Okay, so let's move on to something called Rvalue References. So this part, I'm only going to make you understand this at a high level because this is kind of deep and technical if you go into all the details about it. So I'm not going to ask you to know everything about this, just the fact that they exist. So what is an R-value? So before I talk about R values, I should talk about L values. So all of the variables that you've been making, so like x is equal to 2 times 5, x itself is what is called an L value. The L you should think of as on the left side of the equal sign. But that's not always the case necessarily. But the technical meaning of L value means you can take the address of it. So can we take an address of a variable? Like, yeah, we can just do the ampersand on the variable and then we can get the address of that variable. So that's what it means to be an L value. An R value is basically an unnamed temporary value. So like any literal at all. So if I set x equal to 5, 5 is an R value, okay? So it's a temporary variable that I can't necessarily take the address of it. Okay, I can't take the address of 5 because it's not a variable. So that's what's called an R value, not an L value. Yeah, so here, POW, so this doesn't involve any variables in here. So this is, by definition, an R value, okay? Because it's just some value, and we can't take the address of it, so therefore it's an R value. So an R value reference then is basically just a variable that is a reference to an R value. That's all it is. So it's just the same thing as a reference before with the ampersand, but now it's binded to an R value instead of an L value. So I can show you an example. So if we, for example, make an int x equal 5, and then we can say int reference of y is equal to x, then what is x over here? Is it an L value or an R value? Can I take the address of x? Yes, so it is an L value or an R value? L value, good. So, so y then is, do you think it's an L value reference or an R value reference? With just y itself. Can I take the address of y? Yeah, so is it an L value reference or R value reference? L value reference, good. So, yeah, so here, what we want instead is, I want to bind y to an R value. So here, instead of saying ampersand here, it won't let me do that because I can't bind to what is called a temporary value. Do you have a question? Yeah. Mm-hmm. So essentially what you're asking is, why do we care about R value references or R values in general? Yeah, so we're going to get to that into something that's called the move constructor. But I'm just getting everyone on board on what R value references are so we can get to the thing that it's used for, which is a move constructor. But we'll hit that in a second. So it won't let me do this because 5 is not an L value. Is 5 an L value or an R value? R value, because it's literal, it's a number. So here I have to put double ampersand because I'm binding y here to an R value, and I want y to be a reference, so it has to be an R value reference because I'm binding it to an R value and it's a reference. So it's an R value reference. Okay? Any questions on what R value references mean? Just the definition. Don't worry about what they're actually used for yet. Just do you understand what R value references are? Or does anyone have a question? Okay, so all it means is you have a double ampersand and you bind it to a temporary, so not a variable. Okay, it's just like a number, for example, or a string literal or anything like that. So why do we care about R value references? So remember last time we had this example of this CP class, and what we saw was that we were copying this object all over the place. So I was copying it into a function as a parameter because I'm passing by value, an independent copy. Then when the function returns, I return by value. And so that would do, for what we understand, a copy. And then we did a different copy in a different place. So we're doing a lot of unnecessary copies here. So, and think about what we did. We only had one object present. And throughout the entire example, we never needed an extra copy. But we got extra copies anyway. So think about, like, say, this function right here. Maybe I should get rid of this class. Let's just make this class easier to see. And then maybe we can make a CP class F, which takes, okay, that's fine. And then we make a CP class G, an object called G, and then we do some stuff to G. I don't know necessarily what we're going to do, and then we return G. And then in this, in the main, for example, we can say CP class result is equal to F. So maybe I'm calling this function, it's making an object of CP class, I do stuff on it, it's not really important, and then I return the object. Okay? So why am I making a copy right here at this return statement? Think about what's happening. So G is in this F function, and what we understand now is making a copy of G and then giving that result back to main. Well, think about the original one. Do we need it anymore? No, because look, what is the scope of G? Like, where does G able to be accessed? Within the function. It can't be accessed anywhere else. So when this function goes to return right here, do I need G, the original copy, anymore? No, I only need it back in main. I don't need it in the function anymore. So why are we doing this copy if I actually don't need the original anymore? So that is where move constructors come into play. So what we were doing there is a copy construction operator or copy assignment operator. The point is we're doing a copy. Move assignment and constructors take an Rvalue reference to this object because I'm not going to need this object anymore. It's a temporary. The original one is a temporary. So what we do here is I'm going to move the guts out of this object right here and then paste it over here and not have to have a completely independent copy anymore. Because if we look back at this function, this return statement, right at this point, I'm never going to need G again. I'm going to need the guts of G back into main somehow, either through a copy or a move, but I don't actually need the original anymore. So that's where move constructors are important. So they use what are called Rvalue references, which we just learned, and they're much more efficient because I'm not doing this unnecessary copy anymore, which is kind of nice. So yeah, they use Rvalue references. I'll show you an example. What happens is, if there's any dynamic memory into here, what happens is I reassign them to this, the place where I want them to go, and then in the original object, I set them to null pointer. Okay, so in fact, I don't have an unnecessary copy anymore, which is pretty cool. So how do you actually make this thing? So this is basically what happens. So ignore this no except thing. That's something completely different here. So I have this structure class is the same thing called A, and is it taking an L value or R value reference here? R value reference because it has a double ampersand. Good. So it's taking an R value reference to O. So when this constructor finally finishes, do you think I'm going to need O anymore? No, because I'm moving the contents of this object over to here. So this is, remember the move function. So that actually constructs an R-value reference of whatever you pass into it. So let's see, this object has a string and an int. So it looks like I'm passing the string into move. So how does move work? So what happens in move is whatever is passed in, it casts it to an R-value reference, always. No matter what you give it, it gives you an R-value reference. So because of that, I'm not going to need this object O anymore, I can think, well, the original copy of this string, I'm not going to need it either. I want the original string over to this new object I'm making. So I cast it to an R-value reference, and I construct S in the object that I'm making using the R-value reference constructor there. Okay, the move constructor there. So what happens here is I'm moving the string from here over to here. And then So think about this. Does string have dynamic memory allocation on the inside of it, do you think? Well, think about this. Can a string be any length? Yeah. So do you think it has dynamic memory or no? Think about vector. Does it have a maximum size it can have, or could it just grow as much as we want? It can grow as much as we want. So in fact, a string does have dynamic memory allocation on the inside. Do you think an int does? No, because an int has a fixed size. So I don't need to do any dynamic memory here. I could have dynamic memory if I made it a pointer, but it's not a pointer here. So it's just a regular old int. So there's a function called exchange, but basically what happens is I'm going to move or copy the value k in the original object into the new one and set the original one back to 0. Okay? I'm not really worried about integers because they don't have much memory anyway, but the point is that I'm moving any object that has dynamic memory allocation on the inside, and string is an example. If I had a vector in here, for example, and I wanted to move it over, I want to call move on the vector and then move it over because it has dynamic memory allocation also. Okay? So if we wanted to make a move constructor for our CP class, we would want to have CP class ref, and then other, and then we would want to do anything that we need to in here. So I'm not going to complete the implementation of this because it's almost identical to this one. In fact, it would be identical because we have a string and an int, and this one also has a string and an int. So I didn't even come up with that example. It just worked perfectly. But think about this one. What did the copy constructor take? Not the move constructor, the copy constructor. Well, think about it for a second. If I want to take this object and I want to copy it over to here, should I modify the original, a completely independent copy? No, I don't want to modify the original. So by convention, the copy constructor, okay, come on, Sea Lion, work with me. It's failing already. Okay, so that's not working, but what does the copy constructor take? It takes a const reference to the original object because I don't want to modify the original. Notice, did I put const in the move constructor? No, I did not. Why did I not? Am I modifying the original here? Yeah, what am I doing? I'm taking all of the dynamic memory in this thing and I'm setting them to null pointer. So I am modifying the original here. So that's just something to keep in mind, and I'm not sure what's happening here, but I guess I have to quit and then I'll reload. So just to keep in mind, move constructor does not take const Rvalue references. It just takes an Rvalue reference because we're modifying the original by convention. A copy constructor, because we want to make a completely independent copy, we don't want to modify the original, so it should have a const reference. Okay, so that's all that is really needed here. So this is what the copy constructor should look like. You take a const reference to the other object, and then the move constructor takes a non-const Rvalue reference. Remember, it has the double ampersand. Okay, any questions on the difference between a copy and a move constructor? So why do we have a move constructor, just in general? Yeah.
To move certain actions throughout the program to different places.
Yeah, and so why, could we just achieve the same thing with a copy constructor? Or we could. So why do we have a move constructor? More memory efficient, Ann? Yeah. It's more efficient, right? Because I don't have an independent copy. Okay? So remember, move constructors don't give us any more power than what we had before. It just makes it a lot more efficient. Okay. But of course, we have all these different constructors, and in fact, there are other constructors that you could do. So it's very painful to have to write these constructors yourself, right? And for example, remember that example in the on the web that I showed where you have move of this string over, and then we exchange this int over? What if I happen to not call move on that string, for example? Then what could happen is it calls the copy constructor by accident, and we didn't mean for it to call the copy constructor. Or maybe we call the move constructor by accident and we wanted the copy constructor. So in fact, we could do the wrong thing pretty easily if we're not very precise. So default is actually a very nice thing to help us write these constructors without having to write them. So how would we actually use default here? So instead of having to write everything in these constructors, all you have to say is equals default, and that's it. So the entire copy constructor, unless we need it to do something else interesting, it does the default thing, which is it copies the integer and the string over, and it does exactly what we need. And if we wanted to do the move constructor, we do a very similar thing. I hope that works. Yeah. So we do almost exactly the same thing. We say equals default. And that's really nice. So instead of having all of these different constructors floating around, and we can do this with the default constructor too, which is nice. But it just does the default thing. We don't risk getting anything wrong. It just does the right thing, which is really cool. Think about this, for example. So think of unique pointer. So remember unique pointer? So what is special about a unique pointer? Right, there's only one owner into it. Do I want a copy constructor for a unique pointer? To have two different things point to the same object? No, that's against the rules of unique pointer. So maybe we want to say, I forbid you from using the copy constructor. You can only use the move constructor. So maybe we want to do this for our CP class here. So, but maybe on the inside, I want to do some copy construction, but I'm not going to expose it to the users. So I can't say equals default here because it's exposed to the users. So what is one way that I can make this constructor forbidden to be used? And we've already seen. I can move it into the private section and then that would work just fine. But another way you can use this is instead of using default here, I can use delete. So delete here says essentially the same thing. This constructor is forbidden to be called. So I could move it into the private section or I can use delete here. Either one is fine. So when you're designing classes, you have to think, should the copy constructor make sense in this for this object, or should the move constructor make sense here? So when you're making constructors, you have to think about that sort of thing. Does it make sense or does it not make sense? But yeah, default is really nice when you don't want to have to write the constructor. And the really great thing is that if I have another variable in here, it does the right thing already. So if I had to implement these constructors myself, then I have to change them if I add new data. But default gets everything correct, no matter how much data I put into this object, which is really cool. Okay, any questions about default or delete, but mainly default? So what's the purpose of default? Right, so I don't have to explicitly implement the constructors that we need to. Just do the right thing. We're asking the compiler, make the code for me, and so I don't get it wrong. Yep. Yeah, but yeah, so this last point is interesting, but I'm not going to test on it, but just think about it. If you implement any of the functions, like the copy constructor, you have to implement the move constructor also and all these other constructors for deep reasons, and you can look it up why this is the case. But so my recommendation is make everything default so that you can't get it wrong, but sometimes you absolutely need to do something different in one of the constructors, but that means you have to implement all of them. So that's something to think about there. But let's move on to something called function objects. So this is related to things that we've kind of done before, but also the operator overloading stuff that we talked about. So what we have here is one operator, which is the function call operator, which is the left-right parentheses. And basically what that means is I can treat an object like a function, okay? So here I have a multiply class, and I overload the function call operator, and the function call operator here will take 2 arguments and return the right thing here. So let's just see how you would actually use this. So let's get rid of our CP class because we won't need it anymore. So let's do this. Oops. I need a semicolon there. And then let's just say multiply. So I'm going to make an object called m, and then maybe we'll see out m of 5, 3 like this. Okay, so I'm treating the object like a function, okay, because I'm overloading the function call operator, which is parenthesis, right parenthesis. So of course I could have 3 arguments in here and then modify accordingly, but here I would have to put another argument to match the syntax, and then if I run it, it does exactly what we expect. So I can have any class overload this operator and make it look like a function. So make the object look like a function. So you may be wondering why we actually care about this. So here's an example, basically what we did before. So I can make an instance of the class, and then I can call the function operator on it, and then pass the arguments just like before. So the interesting thing here is, look at this example. So multiply left, right, ignore the 4, 3 part, just the multiply left, right. What that does, if you recall, is that is calling the normal constructor of multiply. Well, there's only one constructor, but it's calling the constructor of multiply, but it's not saving it to a variable. So here we made this multiply prod here. So prod is an object that we create. This is not bound to an object anymore because I didn't assign it to an object. And then we call, but the thing is, it still is an object, but we didn't assign it to a variable. So here I'm calling it on something called an anonymous object. So the object here is anonymous because I'm not saving it to a variable. It doesn't have a name. Whereas this one up here does have a name because it's called prod. So why would you care about, so you think, why are we talking about these anonymous objects versus giving a name to them? So it's something to, that some people in some of the assignments have used before. It's something called a predicate. So what a predicate is a function that returns a Boolean value. And what this is you can pass these function objects into some algorithms in the library, and then it does the right thing. And we'll see examples of this. So a predicate, so it's just basically a function object to perform some task, to return some Boolean value. So maybe a function object, for example, could be, I put bool right here, and I take an int x and int y, and then I return x is greater than y, for example. And so if I pass in an x and a y, it'll tell me whether x is greater than y, for example. So that would be an example of a binary predicate. But we can have unary predicates too, where we just have one argument instead of two. So actually, this is the example. I did not plan this. So very convenient. So this is a class that we can make. We overload the function call operator again. We only have one argument here. So is it a unary predicate or a binary predicate? Unary, because there's only one argument. So I return a bool because I return true or false, and then I return x is greater than 0, for example. So this is a function object that can tell whether some integer is positive or not. Yeah. Great question. We're going to get to that. So you may be wondering, well, we could have just solved all of this with an if statement. Well, why are we making a whole class out of this and then overloading an operator to do exactly what we could have done before? So so here's a binary predicate, nothing special there. So this is where it's actually useful. So we can pass function objects to other functions. Why would you ever care about this? So think of the sort function. So remember assignment 6, where I asked you to, for example, if you have two vectors, and I want you to sort one vector and then also sort the other vector in the same way. Or maybe, for example, we have a list of ASU students. Well, how do I sort ASU students? Well, I could order them by GPA, I can order them by name, I can order them by the ID number, for example. So there are many ways we can order an entire object here. So by overloading the less than operator, for example, then what we could do is pass that along to sort, this predicate along to sort, and it'll sort them in the way that we want it to. So maybe, for example, we could define less than between two ASU students is one GPA of one student is higher than another, for example. Then in sort, what we can say is, okay, I have a vector of ASU students, sort from the beginning to the end, and then the predicate that we pass in is saying, okay, I have two ASU students here, and then the result of it is we want them to be sorted in some order, meaning that one GPA is higher than the other. And then what we can do is, so there is a way to do that called lambdas, and we'll see how to do that. But if we just overload the less than or greater than operator, then we can just pass in as the predicate, just the predicate part, less of ASU student. So let's just see this in action. So I have not done this. I'm very confident something will go wrong, but let's see what happens. So let's make this class called less than, and then maybe we'll have two integers with a bool operator. Okay, never mind. So let's just have less than. Then maybe we can have an int x in here. And then we can say bool operator less than of some other less than object. And then we want to say that our less than object is less than this other one if our own x is less than other.x. Okay, so we can define it this way. We can have many pieces of data possibly. We can have a string in here. We can have other data. But we're going to define less than to mean this one variable right here is less than the other one, the corresponding one over here. So maybe we can have a vector of less than objects here. And then maybe we can, why does this not work? Implicit instantiation of undefined template. yeah, don't do live demos if you have not prepared them. Okay, so let's actually look this up because I don't know the answer. So overload less than operator C++. Okay. This doesn't look like the best website for this, but yeah. Okay. What I wanted to show is this. So if we call sort on vec.begin, vec.end, and then we can say less of the object that we care about, then this won't work either, but for complicated reasons. But what I wanted to show is that we can just pass less in this way, and then what it'll do is say, okay, whenever I want to swap two objects, it'll take a look at the less than operator and then do the right thing. So we don't have to write this complicated thing about, okay, I need to overload this entire sort algorithm and then change it for my one example. By overloading one operator, then I can just pass the corresponding thing to sort, and then it'll sort in the right way. It just calls the less than operator and then swaps the values accordingly depending on whether one was less than the other. Okay? So that's what I wanted to show you, although, so I'll work on this and fix it, yeah. What's there? It's the simplest thing sometimes. Although yeah, this should still not work. Yeah, I'm not sure why. Maybe we can have an int instead, and then let's just see if this works. Oh, okay. Let's just see if it actually works, because I am not confident that it does. So let's just see that this actually works. Okay, so we have to put these extra parentheses in here for complicated reasons. But yeah, so this is what I wanted to show you, is where you can pass in some predicate object. So they define the less equal, greater equal in the standard library for you, because that's usually how we should order things. Either in ascending order, maybe with equality, or greater than in the other direction. So, but of course, you may want to have your own custom sorting, whether it's not just like one is less than the other, maybe something more complicated. But another one is, instead of you just wanting to sort, maybe you want to just remove all the items with some value. So maybe, for example, we can define a predicate here to say, I want to remove all objects that are less than 0 from this integer vector, for example. So I have a vector of integers. Just remove all of the ones that are less than 0 for me. Instead of having me to implement that myself, this would be a lot easier. So these function objects are usually used in sort, but for remove if, you usually provide a predicate yourself. And how do you actually do that? So the way that you can make your own predicate is something called a lambda. So a lambda is basically those function objects, but more compact. That's all it really is. Nothing special here. So it's just a function object, but it's more compact. And why would you care about this? Is that I can insert this as the predicate. So, for example, maybe I want to sort in a different way. So maybe not just one thing less than the other, but maybe one is less than the square of the other, for example. So then what we would do is I copied and pasted the lambda into here. I'll put it on a new line to make it easier to read. So the first argument is the beginning of the vector, or where we want to start from, where we want to end, and then the predicate, which in this case is a lambda. I could have passed less of int in this case, but remember, the sort function looks at two objects in the vector. So the lambda should have two objects being passed into it. So what we want here is, okay, well, we want to say that x is less than y, in this case, if x is less than y times y, for example. And so all you need to do here is return a predicate, so, or really a bool value. So if you return true or false, whatever that is, then if this is false, it'll swap the elements. So I'm not actually sure what'll happen here, but let's see. Okay, maybe it did sort them correctly. But you can see how maybe, for example, we can make this more complicated. I could put any number of statements inside a lambda. So I don't have to just put a return statement here. Maybe I can just say we're comparing the corresponding values. So it doesn't have to be just a return statement here, which is kind of cool. So I could do some modifications if necessary. So here we're saying we're comparing 2 and 1, 5 and 2, 4. So you can do more complicated things in lambdas if you want to. But a lambda is exactly the same thing as a function object, but it's just more compact. Okay? Any questions about lambdas? Yeah. Great question. So what was asked was, what are these square brackets for? So lambdas are really funny. Not in like the ha-ha funny, but like you accidentally shoot yourself in the foot kind of like not really funny thing. So, so what happens here? So maybe we have some constant integer, 10, maybe we'll call it z. So is equal to 10. And then maybe we want to sort only if both x is less than z and y is less than z. Although that shouldn't have worked. Oh, it's because I declared it const. Okay, yeah. So look at here. So I put const here, and everything is fine. But if I remove the const, notice I get errors here, right? So the funny thing about lambdas, so this is one of the pitfalls of C++, is that even though I'm not modifying z in here, it's because it's not declared const, the compiler can't guarantee I'm not going to modify z at some later point. So because lambdas are just function objects, they're not supposed to modify other variables. Because the x and y here are passed into this function object. There shouldn't be any other objects being passed in. So by declaring this const, then essentially what that means is I'm not going to modify this thing, so I can refer to it freely. But if it could, for example, at some point change. So like if I had int z here is equal to 10, I could have said z++ in here because I could have put any value in here. And so the predicate is going to change depending on when I compare two values. So if I compare 2 and 1 at some later point, it may be the case that one of them would swap the two values and the other time would not. So the basic reasoning behind lambdas as function objects here is if you compare two objects right here, no matter when you compare them, it should give you the same value all the way down, no matter when you do it. So if you want to actually do this, you have to put some variable in here. Yeah, so here what this is something called a capture. And in this case, it's called a lambda capture. And so what we're saying here is I'm capturing z, okay? So z right here is being copied into this one. Okay? So this z that I'm highlighting right here, where the lambda starts, is not the same z as this one. Okay? So this z right here is different from this one because we want to have the value not change. So this is something called a lambda capture. Okay? So here, if you want to capture other variables, you put them in here. There are other types of lambda captures, but that's way beyond the scope of this class. And even this is beyond the scope. But basically here, the square brackets just mean if you want to copy values into the lambda to use in the lambda statement, you can do it right here. Yeah. Oh, good question. I don't know. Can I? Yeah, so I can't even do that. I'm not sure if you can. There may be a way, I'm not sure. Good question, I don't know. So let's see. Lambda modify external. So I guess other people want to do the same thing. Maybe we want to say C++. Using out-of-scope variables. Okay, so this might work. So let's just say we want to do our weird thing in here again, and then, nope, that doesn't work. Let's see. Oh, okay, yeah, that's it. Yeah, so here, what do you think this ampersand means in the capture statement? Yeah. So essentially what happens here is I'm copying the reference now. So the ampersand here just means you can copy the reference of any external variable into here. So by doing this, I can capture any variable on the outside and then modify as necessary. And in fact, this solves the const problem of the other statement too. So it's just if you want to actually do this and like you want to get the non-const variable into here, you're free to do so as long as you explicitly say, yeah, I'm copying the reference over. So that's what that is for. So in fact, we can see, let's just see what happens. So let's print the value of z. And then let's just see what happens. Yeah, so we can see that z actually increases here. And then if we print z at the very end, this z right here definitely refers to this z declared before the lambda. So we can actually verify that it wasn't actually copied in. It really was the reference that was copied, and we can see it right here. So it depends on your use case. Usually, you don't want to modify external variables, but sometimes you might. So the ampersand here would help. Yeah. Oh, sorry, I didn't hear. Let's try it. So then maybe it won't sort. Yeah. So that's what actually happens. So let's see. So the first time we go through is we're comparing 2 and 1. We set z to 3. Value is z. So they're both less than 3. So these two halves of this are both true. Maybe let's do x less than y. It's like a normal sort. Yeah, so it still doesn't sort, which is good. So let's see. 2 is not less than 1, so it does do the swap here. 5 is not less than 2, so I guess it keeps the original order. I'm not sure why the arguments are in the wrong order here. Maybe it depends on how the sort works. But if we compare 4 and 5 here, they're both not less than, even though 4 is less than 5, it is not the case that either of them is less than 3. So this returns false. So it doesn't keep the order 4 and 5. So that's why 5 and 4 are in the order in the original vector up here. Okay, so but of course because of this, now the comparison can actually change as we're comparing things, which goes against the morale of doing it, but you can definitely do it. Okay, any other questions before we, yeah? I can't hear you.
How do you now have a function without defining a return type?
I'm not sure what that means. We can talk offline. Okay, make sure to pick up your quiz. They're listed alphabetically by last name.